Okay, let's look at Laplace transforms of cosine omega t and sine omega t. I'm going to start with the Laplace transform of sine omega t. Probably won't completely finish the cosine of omega t. First place, I didn't leave myself enough room. The second place, it's so much like the sine that I'll get it started and you can easily finish it. Now, this is another familiar type of integral. Of course, the definition of the Laplace transform leads us to the integral sine omega t e to the negative st dt. This is a familiar integral, and you should recall that this integral can be done in various ways, but usually by two applications of integration by parts, which leads you to an integral involving the sine omega t e to the negative st on one side, and an integral, a constant times that integral on the other side. You bring them together and solve for the integral. So having said that, hopefully that makes a little sense to you, but whether it does or not, what we're going to do is we can let, it doesn't matter whether we let it doesn't matter which one of these we let equal u, which one we let equal dv. We're going to end up with either an s or omega in our denominator. Let's go ahead and let u equal the sine of omega t, dv equal e to the negative st dt, so that du equals omega cosine of omega t, and v equals negative 1 over s e to the negative st, so that our integral becomes uv, which is negative 1 over s sine of omega t e to the negative st. That will be evaluated between 0 and infinity, and we can see already that at infinity e to the negative st is going to approach 0. At 0, the sine of omega t is going to be 0, so we're not going to get anything from this part. And then it's going to be minus the integral of v du. The v already has a minus, so we're going to write that as 1 over s times the integral from 0 to infinity of, and let's go ahead and put the omega out here too. Okay, it's not very well written. But omega over s times the integral of the cosine of omega t e to the negative st dt. Now that, of course, this one equals 0. We got the omega over s. Write it out decently this time. We're going to make the same kind of breakdown. Our u is going to equal the cosine of omega t dt. Our du will be negative omega times the sine of omega t. Our dv and v will be identical. And we're going to get then negative 1 over s cosine of omega t e to the negative st evaluated between 0 and infinity. And that isn't going to give us 0. When theta equals 0, it's going to give us negative 1 over s, which is going to translate into an omega over s squared. And then it's going to be minus the integral of v du, and I'm looking up here. The u is the cosine of omega t, so that the du is negative omega sine of omega t. We're going to end up with minus omega over s times the integral from 0 to infinity of sine omega t e to the negative st dt. Now, I haven't written out the integration by parts on this, but the integration by parts does give us this breakdown. Now, we get then omega over s squared. The 0 is the lower limit, so we're going to be subtracting, so the negative will give us the positive here. Minus omega squared over s squared times the integral of sine omega t e to the negative st dt. Now, if I've got my sign right on this, I'm pretty sure it's negative because we're getting a negative and there's already a negative, but there's another negative. There are two negatives that come out of the breakdown and a negative because of the integration by parts, and that might not make any sense to you when I'm just waving my hands over it, but again, you can write it out. Okay, so this tells us then that this integral is equal to this minus omega squared over s squared times the same integral. So if I just take this step and put them together, add this term to both sides, what do I get? I get 1 plus omega squared over s squared times the sine of omega t times the integral from 0 to infinity of the sine of omega t e to the negative st equals omega over s squared, so that this integral, which is the Laplace transform of the sine of omega t, is equal to the integral from 0 to infinity sine of omega t e to the negative st dt, and that's going to equal omega over s squared divided by 1 plus omega squared over s squared. This is just s squared plus omega squared over s squared. The reciprocal of that is going to be s squared over s squared plus omega squared, so that this is equal to omega over s squared plus omega squared. Now, I'll write that down in sort of a summary on the next page, but I believe that is the right expression for the Laplace transform of the sine. Now, doing the Laplace transform of the cosine gives us something a little different, and largely because what we get at the first step here on the evaluation between 0 and infinity is not 0 this time. So let's do that much, and then I'll leave it to you to work out the rest of it. But if we let u equal the cosine of omega t and dv equal e to the negative st dt, we get du equals negative omega sine of omega t, and v equals negative 1 over t, 1 over s e to the negative st. And our integral then becomes uv, which is negative 1 over s times cosine of omega t e to the negative st evaluated from 0 to infinity. And then it's minus the integral of v du. Both of these are negative, and we kind of implicitly did that down here as a matter of fact. But this is then going to become minus 1 over s times the integral from 0 to infinity, and I didn't anticipate space very well here. This is really something I expect you to be able to do anyway. No excuse. I made bad use of space here, but if we multiply this out, and of course we get an omega over s here. I forgot the omega as I did last time. Get negative omega over s times the integral of v du, so that's going to be sine of omega t e to the negative st dt. Now that goes on. This integral we've already done, so it's going to be fairly easy to write this out. I just want to point out that this term here, this negative 1 over s cosine of omega t e to the negative st from 0 to infinity, at infinity we still get 0 because the exponential approaches 0. Excuse me, while the cosine remains bounded. At 0 we do get negative 1 over s. So this part of the term gives us a negative 1 over s, which changes the nature of the solution just a little bit. And the result of all this is that the Laplace transform of the sine of omega t equals, as we saw, omega over omega squared plus s squared. And the Laplace transform of the cosine of omega t turns out to be, remember we get where we got a 0 here, we got a negative 1 over s here. That changes things a little bit. And the ultimate result is that we get s over omega squared plus s squared.